Welcome back to our course, Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter Galvin, published by Wiley Publishing. In the last lesson, we examined the round-robin CPU scheduling algorithm and began our investigation of the time quantum. We're going to pick up where we left off and continue our exploration of the time quantum. Turnaround time also depends on the size of the time quantum. As we can see in this figure, the average turnaround time of a set of processes does not necessarily improve as the time quantum size increases. In general, the average turnaround time can be improved if most processes finish their next CPU burst in a single time quantum. For example, given 3 processes of 10 time units each and a quantum of 1 time unit, the average turnaround time is 29. If the time quantum is 10, however, the average turnaround time drops to 20. If the context switch time is added in, the average turnaround time increases even more for smaller time quantum since more context switches are required. Although the time quantum should be large compared to the context switch time, it shouldn't be too large. As we pointed out earlier, if the time quantum is too large, round-robin scheduling degenerates into a first-come, first-served policy. A rule of thumb is that 80% of the CPU burst should be shorter than the time quantum. The shortest job first algorithm is a special case of the general priority scheduling algorithm. A priority is associated with each process and the CPU is allocated to the process with the highest priority. Processes that have equal priority are scheduled in first come, first serve order, and a shortest job first algorithm is simply a priority where the priority is the inverse of the next CPU burst. The larger the CPU burst, the lower the priority, and vice versa. Note that we discuss scheduling in terms of high priority and low priority. Priorities are generally indicated by some fixed range of numbers like 0 to 10. However, there is no general agreement on whether 0 is the lowest or the highest priority. Some systems use low numbers to represent low priority. Others use low numbers to represent high priority. This difference can be confusing. Our authors have chosen to represent low numbers as the highest priority, so a short CPU burst time is higher priority than a long CPU burst time. Priorities can be defined either internally or externally. Internally defined priorities use some measurable quantity or quantities to compute the priority of a process. For example, time units, memory requirements, the number of open files, the ratio of average input-output burst to the average CPU burst have all been used in computing priorities. External priorities are set by criteria outside of the operating system, such as the importance of the process, the type and the amount of funds being paid for computer use, the department sponsoring the work, and other often political factors. Priority scheduling can be either preemptive or non-preemptive. When a process arrives at the ready queue, its priority is compared with the priority of the currently running process. A preemptive priority scheduling algorithm will preempt the CPU if the priority of the newly arrived process is higher than the one that's running. A non-preemptive priority scheduling algorithm will simply put the new process at the head of the ready queue. A major problem with priority scheduling algorithms is indefinite blocking or starvation. A process that's ready to run but waiting for the CPU can be considered as blocked. A priority scheduling algorithm can leave some low priority processes waiting indefinitely. In a heavily loaded computer system, a steady stream of higher priority processes can prevent a low priority process from ever getting the CPU. Do you remember that example of shortest job next that I mentioned earlier? Generally, one of two things will happen. Either the process will eventually run, such as when everybody else goes home for the day and there's no activity, or the computer system will eventually crash and lose all unfinished priority processes. It could be possible that a low priority job might not run for a long, long time. A solution to the problem of indefinite blockage, or indefinite postponement as it's called by other authors, is aging. Aging involves gradually increasing the priority of the processes that wait in the system for a long time. For example, a low priority job could periodically have its priority increased every few cycles until it eventually moves to the top of the queue. Eventually, even a process with the lowest initial priority would have the highest priority in the system and would be executed. In fact, it might only take minutes for the low priority job to age to a priority 0 job. Another option is to combine round robin and priority scheduling in such a way that the system executes the highest priority process and runs processes with the same priority using round robin scheduling. Look at this set of processes with the burst time in milliseconds. Using priority scheduling with round robin for processes with equal priority, we would schedule these processes according to this Gantt chart using a time quantum of 2 seconds. In this example, process 4 has the highest priority, so it will run to completion. Processes P2 and P3 will have the next highest priority, and they will execute in a round robin fashion. Notice that when process 2 finishes at time 16, process 3 is the highest priority process, so it will run until it completes execution. Now only processes P1 and P5 remain, and as they have equal priority, they will execute in a round robin until they complete. In this lesson, we finished our discussion of the time quantum. We explored another CPU scheduling algorithm called priority scheduling, and we also investigated the issues of aging and starvation. Next, we will move into multi-queue CPU scheduling algorithm. So let's take a break here, go over your notes, take care of any business you need to take care of, and when you're ready, come on back and we will take a look at multi-queue CPU scheduling.